Hello students, in the present video lecture, we'll try to cover some topics like numbers, arithmetic operations and characters. Computers operate on the information which is represented by two valued electrical signals labeled as 0 and 1. So always the patterns of 0 which represents low value. If it is 1, that means value is high. We define the amount of information represented by such a signal as binary digit. It is nothing but binary digit. A string of bits is called as binary numbers. A binary number can represent the value of an actual number. Either the actual number value is given in terms of hexa or BCD or binary format, or a text character or an instruction code, depending on the type of application which is used. So we can have three different formats by which any numbers can be represented. That means numbers can be represented in three formats. The first format is sign and magnitude. The second format is ones complement method, and third format is twos complement method. In all three formats, MSB for positive number and MSB value will be negative for negative number. So in general, we can represent any n-bit binary vector as b is equal to bn minus 1, bn minus 2 and so on, b1, b0. So irrespective of the number, we can have either the number is positive, that means the positive number, the value of MSB will be equal to 0, the number is positive. If the value of MSB is equal to 1, that means the number is a negative number. So in a case of sign and magnitude system, negative value is obtained by changing the MSB from 0 to 1. As I mentioned before, the value of MSB, it will decide whether the number is positive number or else negative number. So in the case of sign and magnitude, we can get the negative number by changing the MSB from 0 to 1. You can change the MSB value from 0 to 1. That means we can represent a given positive number in terms of negative magnitude. For example, plus 5. So in terms of binary, I can write it as 101, that is 5. Since it is plus, I can take the MSB value as 0. And so now I need to represent this plus 5 in terms of sign and magnitude. So suppose I need to represent minus 5. So first I'll write magnitude as it is, that is 101. And since it is negative, I can change 0, that is the MSB is 0 here. So instead of that, I can consider it as 1. So now the number becomes minus 5. So plus 5 means 0, 1, 0, 1. Minus 5 means 1, 1, 0, 1. In the case of sign and magnitude, negative value is obtained by changing the MSB from 0 to 1 of the corresponding positive value. So next comes ones complement system. Negative values are obtained by complementing each bit of the corresponding positive number. For example, Minus 5 is obtained by complementing each bit in plus 5. So suppose plus 5, we can write it as 0, 1, 0, 1. So now we can complement each bit 0, 1, 0, 1. So this is nothing but 1's complement of plus 5. 1's complement of plus 5 we can obtain by complementing each and every bit. In other words, the operation of forming the 1's complement of a given number is equivalent to subtracting that number from 2 to the power n minus 1. 2 to the power n minus 1. So next is 2's complement method. Generally, 2's complement method can be obtained by adding we already computed 1's complement value. So you can just add 1 to 1's complement value and that will compute the 2's complement of the respective number. So in the case of 2's complement method, the negative number is obtained by getting the 2's complement of the corresponding positive number. This operation is same as subtracting the positive number from 2 power n. So we can also get the 2's complement value by subtracting the respective number from 2 power n. So in the case of 1's complement of 5, so 1's complement of 5, we already having it as 1 0 1 0. So you can consider plus 1 to 1's complement of 5. So in order to get the 2's complement of 5. So that is 1 0 1 1. So the 2's complement of the system can be obtained by subtracting the positive number from 2 power n, or else we can compute 1's complement first and we can add 1 to 1's complement value. So that means the 2's complement of the system, that means 1's complement of the number plus 1. 1's complement of the number plus 1. So here we can observe that binary signed integer representation. So we are having different numbers and the respective sign and magnitude, 1's complement representation as well as 2's complement representation is shown in the diagram. So we can observe that in the case of positive numbers, it is not necessary that we have to convert that into 1's complement as well as 2's complement method. So till here, so that is this one. So whatever the number we are writing, since it is positive, so this is plus 7, plus 6, plus 5, plus 4, plus 3, plus 2, plus 1, plus 0. So since the numbers are positive, so we can write as it is irrespective of the system representation is sign and magnitude, 1's complement method as well as 2's complement method. But in the case of negative number, so this is nothing but 0. 0 0 0 means 0. Since the sign is 1, so I can write it as minus 0. Similarly, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. So 1's complement of minus 0. So since if you are having minus 0 means 1, 0, 0, 0. So now I am not considering the sign bit. So I will complement the other bits 1, 1, 1. So what is the magnitude? That is 7. So since the MSB bit is 1, minus 7. So similarly we will get minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, minus 0. So after that we can complement to 2's complement means 1's complement plus 1. So that is 1, 1, 1, 1 plus 1. 0, 0, 0, 0. It is 1, 0. So we can get minus 8. We can get minus 8. So this is the value minus 8. Similarly, you will get minus 6 means equivalent to minus 6, minus 5 means minus 6, minus 4, minus 3, minus 2 and minus 1. Addition of positive numbers. While adding two 1-bit numbers, the sum of 1 and 1 requires 2-bit vectors 1, 0 to represent the value. We say that sum is 0 and carry is 1, and the carry will be equal to 1. So here, we can consider different numbers, 2-bit numbers. 0 plus 0 will get sum as 0. So 1 plus 0 will get sum as 1. Similarly, 0 plus 1 will get sum as 1. Similarly, 1 plus 1, sum is 0 and carry is 1. So that is nothing but carry out. Addition and subtraction of signed numbers. Following are two rules for addition and subtraction of n-bit signed numbers using 2's complement representation system. The first rule is to add two numbers, add their n bits and ignore the carry out signal from the MSB position. Result will be algebraically correct if it lies in the range from minus 2 power n minus 1 to 2 power n minus 1 minus 1. So we can say that as per the first rule, add first two numbers, and while adding those two numbers, first we have to add their n bits, ignore the carry out signal from the MSB position. So as per the second rule, to subtract two numbers x and y, that means we have to perform x minus y. So while subtracting, what we can do is, so we can x plus minus y we can perform. So that is x plus 2's complement of y. So while subtracting, we can consider x plus 2's complement of y. So that will be equivalent to x minus y. So that is the second rule. In order to subtract two numbers x and y, take the 2's complement of y and add to x. When the result of an arithmetic operation is outside the representable range, an arithmetic overflow is said to occur. So whenever after performing arithmetic operation is outside the representable range, if it is outside the representable range, then arithmetic overflow is said to occur. To represent a signed 2's complement form using a larger number of bits, repeat the sign bit as many times as needed to the left. This operation is called as sign extension. So here, suppose if I am having minus 7. So minus 7 magnitude is 1, 1, 1 and minus 7 is 1, 1, 1, 1, 1. But I have to perform, so this is 4-bit operation. So this is, I can consider it as 4-bit number. But I have to perform addition with 5-bit number, one more number. So at that instant, can directly expand the sign bit. I can take additional bits to the left side. So this operation is called as sign extension. In one's complement representation, the result is obtained after an addition operation is not always correct. The carry out cannot be ignored. So always after performing the operation, if you are neglecting the carry out, I can say that the addition operation will not be correct. So if C is equal to 0, the result obtained will be correct. Since there is no carry out. If there is no carry out, the obtained result may be correct. But if carry out occurs, then 1 must be added to the result to make it correct. So if there is a carry out, what we can do is, so we have to add this carry out along with the resultant in order to make the result as correct. So if there is no carry, so we can ignore the carry out. That means since C is equal to 0, but if C is equal to 1, then a 1 must be added to the result to make it correct. Overflow in integer arithmetics. When result of an arithmetic operation is obtained, the representable range. So if it is outside the representable range, that means arithmetic overflow is said to occur. For example, if you add two numbers plus 7 and plus 4, then the output yes is equal to, so I can consider plus 7, that is 0, 1, 1, 1, and plus 4 is nothing but 1, 0, 0 and 0. So I can compute the sum 1, 1, 1 and 0. That is 1 plus 1, 1 plus 1 is 0 and 1. So here I can say that which is the code for minus 5 and incorrect result. So this is equivalent to minus 5 and the value 7 plus 4 I have to get it as 11 plus 11. But the actual computed value is equivalent to minus 5 also. An overflow occurs in following two cases. The overflow occurs only when adding two numbers that have the same sign. So I can say that overflow may occur if you are adding two numbers of same sign, or else the carry out signal from the sign bit position is not a sufficient indicator of overflow when adding the signed numbers. Number representation formats. So first we'll consider B. The second column is sign and magnitude. So that is one's complement method. Last column is two's complement method. So first we'll consider number 0, 1, 1, 1. So since the MSP is 0, sign and magnitude I can write it as plus 7. Since the number is positive number, one's complement is same as sign and magnitude. Two's complement is also same as sign and magnitude. That is plus 7 and plus 7. So next we'll consider the second number, that is 0, 0, 1, 1, 0. So magnitude is 6 and sign is positive. Since the number is positive, plus 6. So next we can consider 5, that is 0, 1, 0, 1. So that is plus 5, plus 5, plus 5. So next we can consider 0, 0, 1, 0, 0. So that is plus 4, plus 4 and plus 4. So next we can consider 0, 0, 1, 1. 0, 0, 1, 1. So I can take it as plus 3, sign and magnitude plus 3. 1's complement is also same. This is also same. Next we can take plus 2, that is 0, 0, 1, 0. 0, 0, 1, 0. Since the number is magnitude is 2, sign is 0 means plus, 2's complement plus 2. 1's complement as well as 2's complement both are plus 2. So next is plus 1, that is 0, 0, 0, 1. So that is plus 1, plus 1, plus 1. So next we can consider 0, 0, 0, 0. Magnitude is 0, sign is plus, and here also plus 0, plus 0. So we'll consider B as 1, 0, 0, 0. So that means magnitude is 0, sign is minus, that is minus 0. So now we have to represent using 1's complement method. So that means I'll take the magnitude, I'll complement the magnitude 1, 1, 1. So that is 0 is nothing but 1, 0 is nothing but 1, 0 is nothing but 1. And I'll keep write sign as it is. So that is minus 7. That means minus 7. So next I'll take 1's complement plus 1, that is 2's complement of the number. So I'll take the magnitude 1, 1, 1 plus 1. So that is 1 plus 1 is 0, 0, 0, 1. So this is nothing but 8, and I have the sign bit as 1. So that means minus 8. That means minus 8. Similarly, we can take the next number, that is 1, 0, 0, 1. So if I am taking just magnitude, that is 1, and since the sign is negative, so I'll take it as minus 1. So now, I'll take the magnitude, that is 0, 0, 1. So I'll complement each bit 1, 1, 0. So that means 6, and sign of the number have not considered while complementing. So that is minus, that is 1, 1. That means minus 6. Once again, we can write the 2's complement of the number. So 1's complement of the number is minus 6. So I'll take only the magnitude which is complemented, that is 1, 1, 0 plus 1. So that is 1, 1, 1. The magnitude is minus 7, magnitude is 7, and the sign I have preserved, that is minus 7. Similarly, we can take the next number as 1, 0, 1, 0. So the magnitude is 2 and sign is minus. So now I'll just consider the magnitude. I'll preserve the sign as it is. So magnitude is 0, 1, 0. So complement each bit 1, 0, 1. So I'll get 5. I have preserved the sign bit, that is minus. minus 5. So now using 2's complement representation, I'll take the magnitude as it is 1, 0, 1 which is complemented plus 1, 1 plus 1 is 0, 1, 1. So that is got the value as 6 and have preserved the magnitude. I preserve the sign of the number, that is minus 6. So similarly we can take the next number as 1, 0, 1, 1. So what is the magnitude? Magnitude is 3, sign is minus. So in 2's complement we will get the value as minus 4, and using in 1's complement you will get the value as minus 4, and 2's complement you will get the value as minus 5. Similarly the next number, that is 1, 1, 1, 0, 0, magnitude is 4 and sign is minus. So in 1's complement method you will get the value as minus 3, and 2's complement method you will get the value as minus 4. And so on. Arithmetic overflow. The rules for detecting overflow in 2's complement sum are simple. First one, if the sum of two positive numbers yields a negative result, the sum has overflowed. The second rule is if the sum of two negative numbers yields a positive result, the sum has overflowed. Otherwise, sum has not overflowed. That means overflow may occur if you are adding any two positive numbers. If you are adding any two positive numbers, positive and positive numbers, but the result is negative. That is rule 1. Or else, if you are adding any two negative numbers, and you will get the positive result. So if the sum of two positive numbers or two negative numbers may yield a negative result or a positive result, then sum has overflowed. Otherwise, sum has not overflowed. So we will consider some example. First we will consider simple example in order to add two numbers, that is plus 3 and plus 4. So in binary we can write plus 3 as 3 is nothing but 0, 1, 1. Since it is plus, consider the sign extension as 0. 4 means 1, 0, 0. Since it is plus means sign extension as 0. So now add these two numbers 1, 1, 1 and 0. So here that means the value is plus 7. I can say that here we added two positive numbers. I can observe that the MSB bit of the first number is 0, that is positive. The second number is also 0 and the result is also 0. So then I can say that there is no overflow. No overflow. So we'll consider one more example. So we have to add two numbers, that is plus 5 and plus 6. So 5 I can write it as 1, 0, 1. Since it is plus, MSB bit is 0. And 6 we can write it as 1, 1, 0. Since it is plus, MSB bit is 0. Perform the addition 1, 1, 1 plus 1 is 0 and 1. So here we can observe that the MSB bit of the first number is 0. This is also 0, but MSB bit of the result is 1. So that means we added two positive numbers we added two positive numbers, but the result is negative. Then I can say that there is a occurrence of overflow and the result is incorrect. Result is incorrect. So overflow may occur if you are adding two positive numbers and the result may be negative. Else, if you are adding any two negative numbers and the result will be positive, then only overflow may occur. Take the next example. So we have to add plus 5 minus 7. Plus 5 we can write it as 0, 1, 0, 1. Minus 7 we can write it as, first I will take plus 7. So that means 0, 1, 1, 1. So now I will take 1's complement of that number 0, 0, 0, 1. So plus 1. So that is 1, 0, 0, 1. So that is nothing but minus 7. So plus 5, that is 0, 1, 0, 1. Minus 7 is 1, 0, 0, 1. So we have to perform addition. So that means 1 plus 1 is 0. Here it is 1. Here it is 1. Here it is 1. So here we added one positive number and one more is negative number. The result is also negative, but there is no overflow. There is no overflow. So overflow may occur if you are adding any two same sign numbers, either positive or negative, which may result in, if you are adding two positive numbers, the result may be negative, or else if you are adding two negative numbers and result may be positive, then only overflow may occur. So we will take one more example. We have to add minus 6 plus minus 7. So minus 6, so first I will take plus 6. So that is 0, 1, 1, 0. So I will complement all the bits including sign bit 1, 0, 0, 1 plus 1. 1 plus 1 is 0, 1, 0, 1. So this is nothing but minus 6. So similarly I will take minus 7. Minus 7 we already computed, that is 1 minus 7, that means 1, 0, 0, 1. So we have to perform minus 6 plus 7. So that is 1, 0, 1, 0 plus 1, 0, 0, 1. So 1, 1, 0, 0, 1. So check the MSB bit. Here it is 1, here it is 1. That means both the numbers are negative, but MSB bit is positive. So I can say that overflow occurred and result is incorrect. Similarly, we will take the next example, that is plus 2 and minus 5. So plus 2 we can write it as 0, 0, 1, 0. Minus 5 we can write it as 1, 0, 1, 1. And can add these two numbers 1, 0, 1, 1. And the result is minus 3. There is no overflow. So next I will take plus 3 and plus 7. Plus 3 and plus 7. Plus 3 means 0, 0, 1, 1. Plus 7 means 0, 1, 1, 1. So 0, 1, 0, 1. So result is minus 6. So here it is positive, here it is positive, and the result is negative. So therefore overflow occurred. Similarly, we can consider next example as -7 plus 4. -7 we can write it as 1 0 0 1, plus 4 is 0 1 0 0. So we'll get the result as 1 0 1 1, that is equal to -3. There is no overflow. So next I will then consider plus 6 plus 2. Plus 6 means 0 1 1 0. Plus 2 means 0 0 1 0. So on addition you will get 0 0 0 1. That means this number, sign of the number, this is positive, but the sign of the result is negative. Then overflow will occur. So the next example is plus 2 plus 4. 2 means 0 0 1 0. 4 means 0 1 0 0. We will get 0 1 1 0. So since this is positive, both the numbers are positive, result is also positive. So this is equivalent to plus 6, no overflow. So this is how we can compute and we can check whether arithmetic overflow occurred after performing addition operation with respect to a given two-sign integer.